We start this notebook with an example, and in this example we want to design a warped low-pass filter with cutoff frequency of 0.5 times pi, where pi is the Nyquist frequency. So here we have half the Nyquist frequency, and here this frequency is the end of the passband, with frequency warping close to the Bark scale of human hearing. Before we do this, for a comparison, we'll design an unwarped filter with 4 coefficients with these specifications. So here we are importing SciPy signal, we are importing matplotlib to plot, and here we are using the Remez algorithm. Note that the Remez is normalizing to sampling frequency equals to 1, and here we will have our Remez filter. So this is the unwarped filter coefficients calculated with the Remez algorithm using these specifications here. So 0.5 pi is the cutoff frequency. We have here the coefficients. We can take a look at the frequency response. So using SciPy FracZ, so we're plotting here the frequency response of these unwarped filter coefficients, and this is the frequency response. We can see that this is not a good filter. The passband is too wide and there is almost no stop band attenuation. So this filter is probably useless for our application. So next step, we will design the FIR low-pass filter of 4th order, which we then want to frequency warp in the next step with a warped cutoff frequency. So first thing we need to do is we have to compute the all-pass coefficient for our all-pass filter, which results in an approximate Bark warping. So this equation here comes from this paper, Bark and ERB bilinear transform. So it's equation number 26. You can download this paper from this link here. And here Fs is the sampling frequency in kilohertz. And then we need to use this for our warp design. So what we're doing here now, we have this warping phase. This produces a phase for an all-pass filter. It takes as an argument the input vector of normalized frequencies from 0 to pi and the all-pass coefficient. So the all-pass coefficient is calculated from this equation here that you find in this paper. You can download here. You can read and see is equation number 26. So we are defining here this all-pass coefficient. Then we are calling this warping phase, and we have our warped cutoff frequency. Then we need to normalize to 2 pi to use with the Remez algorithm. So we're doing here, and now we are calling the Remez algorithm with this new cutoff frequency that we calculated after all these procedures, and we have these filter coefficients in the warped domain. Here A is the warping all-pass coefficient, FCW is the warped cutoff frequency. Then we normalize the cutoff frequency to 2 pi. We have here use this the input for the Remez algorithm, and it gives us the filter coefficients now in the warp domain.